Well, that's true.
I'm always Grimmer is like the biggest competition.
Yeah,
You put like a rich doctor.
It's impressive. I've been surprised at Johnny.
You have not.
This is deserves a good policy.
Yeah, I thought.
Show you. Then it just keeps it in the.
It's not. It turned out to be a good idea to go to the panel after all.
You get good feedback from
Well, that's right.
Yeah, you gotta
It was surprisingly very fun.
most of it is, like, there's a lot that changes in the paper, not so much in
But
Not
not
about the top.
Obviously,
Yeah.
not the
essentially
style,
the
like,
policy itself had shown
change the way they present it, but yeah. we have a lot of different things to do.
Well, I was watching.
Yeah.
I mean, the talk is always just gonna be like, here's the main figures, like, right, like, here's the main.
Yeah, I watched Fox all the
Here's the justification to the project, that's it. So the feedback was like very, it was all like very,
Yeah.
bringing feedback on this check, and lots of other stuff.
And then we've done like lightning rounds. Gary's had like extensive email correspondences with various people. And he's like English language in a bunch of different places.
You don't
Yeah, I think part of the challenge for us is trying to
you have to, if it's
trying
not
to
just
write this in a way that's actually useful.
last year when they
The ultimate goal in sometimes is to get implemented rather than having methodology. Now, that's gonna be, that's part of the pitch of the paper is what you're doing now is kind of, maybe, but you can't, I mean, you need to take.
there was some theoretical.
Yes.
I mean, I think part of it is in the course, right? It's like, putting this paper submission publicity that like our colleagues who would come back for witnesses.
Yeah.
Which seems really, because all you need is shape buttons, right? Like,
If you're 12 authors.
well, in order to
Yeah, you should-
how to do like making stuff in art. But you can also like run them on a subset.
Definitely, there's a follow-up project, which I'm gonna have to do almost by myself, which is like, I have to figure out how to get all the ArcPy code to be wrapped in R, and then have like an easy web interface where you can just give it a shape file and it'll do the rest. Except it'll take like 25 or 30 minutes to do like ArcPy. I mean, there's a lot of steps, right?
Yeah, I'm down.
You know, one of those steps is just like take the shape file and turn it into a raster image and then convert it into a bitmap and then run it through Harris Corner. There's just like one.
I made like a test account that was like a test, you know, test room on passwords. I went through before, this was really dumb. And someone logged into it and started to my it isn't bad. Like I couldn't believe it. Wait, okay, so you had one account that had a terrible password. Yeah, that had access. It was like the only thing that had it was like an administrator account. No, so it wasn't. Luckily, it was not an administrator. But it was a test account that I used to test student stuff on. I got access to it. But so does this mean like she's like a lot of questions? So is this like really good to sit out there and look for rules? I think there's like multiple ways of doing it. And what is Bitcoin? So like the way that Bitcoin works is like I just barely know anything about it. So the way I understand it works is basically take a and just like run doing notes.
You need to
Right, yeah, because
Everyone's flying fast. Yeah.
But it takes a computing power to get it.
Yeah.
Yeah. And so somebody, when they hack this, is looking for computing power to get Bitcoin. They just sign up and start like run a process. I got an idea that's like they're using like 4,000% of the CPU. And so I'm like, yeah, no, that's not right. I was like, I was at first I thought it was like some one of the students had gotten on and like was doing like I don't know, like trying to import like full file census or something. But did you got some notifications that this is amazing. Yeah, it was kind of I was
Right
kind of blown
now,
away.
much less. That's part of the thing I want to do.
No, someone hacked my
Historically, there was huge one.
installed.
Because it was personal colony, all this shit.
Yeah, there you go. Well, I mean, this was really like as bad as that was. I don't know, man. I kind of think it seems like that would have been an okay place to use people in account. I think I didn't realize that. Well, I just don't know how they reach.
I don't know.
Well, they count.
Oh, yes.
Some of these big gifts.
So you had the same party.
I think so.
And then they just
I'll keep an eye on it.
default.
There's probably stuff
So
that's
that's like.
remember this conversation we had pretty
until the last time, when Portugal very quickly built a very strong party, and Brazil continued so right now they are different, and they have that's what I'm trying to historical. They were
They can.
You want some?
I'll just try to route.
Chris, how you doing?
I think we got it.
That's good. Got a lot done. I think it's one of the first times we had where I was like, wow, I was really productive this summer. Doesn't lot happen. What's that?
So politically, from all the way to build parties very quickly, and they do it very well. So the party that we select, the party still control politically.
Yeah, we did our market.
I think that's what Chris said.
Oh, yeah. That's
I just heard your Ken Bowles, I didn't catch what he said after.
University of North
University of North Carolina, I see, yeah. I know you're here for the semester, is that right?
It is.
Okay, good. Yeah, yeah.
Some parties are much.
What level is he here? Or is it just
It should be Dan.
Yeah.
So I'm interested in invitation. Appreciate it.
All right, let's get started. Welcome everybody to the first session of Applied Science this year. Due to some scheduling issues, we've changed speakers, but we're excited to welcome Mayya and Aaron, who graciously volunteered to present their work in progress with less than 24 hours notice. So let's give them, a lot of credit for that. Let me know, email me at danahiggins@fas.harvard.edu if you want to be added to the listserv and you are not currently. But other than that, just enjoy the food and let's get started.
Thanks, Dana. I'm Maya. I guess I'm a longtime listener and first-time caller to this workshop, so thank you for having me. Gary wanted to make sure that we told you that he was very sorry he couldn't be here, but he is typically here. We've been working on this paper for a while, so we're excited to have results and excited to hear what you think about this paper. So with that, let's get started. This paper at its core is really about districting, which it turns out is pretty fundamental to democracy. And the reason for that is that whoever happens to be in control of districting is in control of the fundamental units of representation, right? If you get to draw the map, you get to dictate what the body of legislators at any level looks like that comes out of that map of districts. Okay? And for that reason, there are hundreds of millions of dollars spent in the US trying to influence the rules of the game, the way these districts are drawn. There's litigation over districting in almost every jurisdiction, at every level of government, in almost every time period. Some of it is ongoing for maps that were drawn 20 years ago. Okay. Redistricting is frequently blamed for unfair elections, unfair outcomes, excessive partisanship, policy gridlock, partisan bias, lack of electoral responsiveness, racial bias, and all the other ills of democracy. There's a story you might have seen recently about North Carolina about a legislator who had his district gerrymandered to include his second home. So there's like a branch drawn out to encapsulate his new house. So you see this type of gerrymandering practice and districting blamed for outcomes for reasons like this. So the question becomes, okay, how do we fix this? If we know that these types of things go on in the districting process, what do we do? And the received wisdom for that has been to constrain the redistrictors, right? Don't let them draw the maps that they want to protect themselves. So people suggested things like population equality, enforcing population equality requirements across districts, enforcing partisan fairness requirements across districts, racial fairness requirements, ensuring that people respect municipal boundaries and communities of interest that really should be together and not split into multiple districts if they live in one city or something like this. And they've suggested requiring, more than suggested, they've encoded legally requirements for compactness, right? They've required that the districts drawn in legislative maps be compact. So the question is, what does that mean? And that's part of what this talk is going to focus on. This is an area, compactness namely, where political scientists have contributed a lot to the real world. So political scientists have invented the standard of partisan symmetry that's sort of used to evaluate fairness of elections in litigation, other cases. They have invented methods of ecological inference and other tools to assess racial fairness and racial equality across districting and election outcomes. They have found ways to forecast elections in new districts that haven't even been drawn yet. And they do a lot of public service. Political scientists actually testify as consultants to people who are drawing maps. They testify as expert witnesses. They are special masters who actually work a lot in the real world in the process of district litigation and drawing districts. And they've had a measurable impact on the way people think about compactness and other parts of districting across legal cases and state law. So for instance, the standards that lawyers often use to evaluate compactness come from political science. Okay. But there's a disconnect between political science, the discipline, and the real world over this particular issue of compactness. In particular, political scientists, when tasked with the defining compactness and finding ways to measure it and implement standards for compactness and districting, have said that compactness is so complicated, there are so many features that really are compactness, that we need hundreds of measures to analyze compactness. We've found like ways to calculate compactness hundreds of different ways, and all of them are valid, and we've divided this idea into so many dimensions and calculated them all. But the law assumes that compactness is so simple, there's no definition needed. That's sort of an unfair way to phrase this to the law, but generally what we mean is that the law assumes that there is some intuitive dimension of compactness, right? You and I can look at a district, we can decide by looking at it whether it's compact or not. And there's some essence of this idea of whether or not districts are compact that we can all see and share and understand the same way. Okay. And it is true that definitions of compactness in the law are pretty open-ended. So for instance, most state constitutions across the United States require that districts be compact when they're drawn pretty explicitly. But when they do that, the definitions of compactness that they use look kind of like this. If you look at the Illinois Constitution and you try to figure out what compactness actually means when you're trying to draw districts, this is all you get. The Illinois Constitution says legislative districts shall be compact, which is super helpful. Okay, if you try to get more information on this definition, you look at the state of Washington, for instance, their constitution says each district shall be as compact as possible, which is great. Impossible districts are out. Don't draw impossible districts. A lot closer to the truth. Okay, if we look at Iowa, Iowa says avoid drawing districts that are like oddly shaped. Don't do that. Great. That's super helpful. The Supreme Court
has weighed in on this and said that one need not use Justice Stewart's classic definition of obscenity, I know it when I see it, to recognize that dramatically irregular shapes may have sufficient probative force to call for an explanation. So think about what that says. The Supreme Court here is saying that we don't want to fall back on this subjective standard of like, I know a non-compact district when I see it, but if I see a weird district, I know that's not compact. That's how we should actually think about this. And there's actually a lot of precedent in the, reading decisions in Beef v. Jubileer and other recent Supreme Court cases about compactness. There's a real tension because the Supreme Court seems to really want an objective standard for compactness, but there's this tension because political scientists have made up like 100 of them. So the question becomes what to write, and do we throw out all of these standards and eyeball it? What do we do in the end? So the Supreme Court wants there to be some sort of objective statistical standard for compactness, but there are too many options, and that often leads to all of those options being thrown out. Okay, so compactness is required in lots of other jurisdictions, not just state constitutions, lower and higher levels of governments. So it matters. It's always going to be litigated. It's not going away. So we have to find a way to reconcile this tension between political science, just tons of standards, and the law, which wants one. So in the law, it's assumed that compactness has a simple single dimension that you know when you see. So in other words, when laws are written, they assume, right, that we can take a bunch of districts and arrange them on an axis like this, right, with one side more compact and one side less compact, and we can take a district like this, which looks like a pretty compact square, and we can put it here. We can look at another district that looks like this, also pretty good, except for this thing jutting out here, so maybe that's less compact than this. We can take a district like this and say that it's worse than these, it's a little bit worse than these two, and a district like this is going to be worse than all of these, right? So we can generally do this. That's what's assumed in the law, that there's some essence that compactness has that we can all perceive. Okay. This paper is going to argue that that exists. There is an intuitive dimension like this, and that's going to be a clear difference between a lot of the compactness standards that are used in courts today, because all they do, and we'll go through examples of these types of standards in a little bit, but they take some piece of information about the shape of a district, like how round is it, how many radial arms does it have, and they convey that information, so you can use that to measure compactness, but is that really compactness in the sense that the court wants? We don't know, but the court does want, the court does assume that there's some dimension we can organize districts like, and this paper is going to argue that that's true. But the question becomes, how do we estimate where a new district that we haven't seen yet, because it hasn't been drawn, falls on a continuum like this, right? That's the challenge. How do we assess new district maps according to this dimension? So that's sort of the big picture goal of this paper. We need a consensus measure that will take districts, right? Districts that we've seen and districts that we haven't seen yet, and arrange them along some sort of compactness dimension that the law recognizes that we all see the same way. So that's the big picture goal of this paper. We're going to take a model, we're going to feed it a lot of information about what these districts look like and all of their their geometric features, and we're going to train this model to respond the way that people respond to this model when they are asked to arrange all of those districts along this dimension of compactness. We're going to boil all of those features of district shapes down, and we're going to basically build a model that evaluates the compactness of districts the way that you would. Okay, but before we get into the details of how we do that, let's start by reviewing some of these existing measures that social scientists have used to evaluate compactness, and talk about why we actually need something like this. Like, what are the existing measures that people use? What's wrong with them? Why would we bother doing something like this? So here's an example of one measure of compactness that political scientists have used and that have been used in the courts to evaluate compactness. Okay, it's just the length-width ratio of a minimum bounding box. The intuition behind this is just that square districts are more compact than long, thin districts. Okay, so if I wanted to measure this, I would grab a pair of districts, I would draw the minimum bounding box around each district, and I would take the length of the district and the width of the district along these axes, and I would take the ratio, right? If I did that for these two districts, for instance, these are all, the districts that you're going to see in this are images of their real districts. They're, I think all these are state legislative districts, but they're from the main data. These are all real, but using the length-width measure for these two districts would tell you that they're equally compact. So this district that looks like a square but with a sort of a ragged border, and this district that kind of looks like a flexing arm, equally compact in the views of length-width. It might be a tough sell. Okay? So that's one shortcoming of this length-width ratio measure, but that's something that's pretty widely used. Probably the most common measure of compactness that you see used in legal cases is REOC. And REOC is based on the intuition that circular districts are the most compact districts. Okay, the ideal compact geometry is a circle. So what REOC does is just take the area of a district and divide that by the area of the minimum bounding circle around that district. So I would take these two districts, if I wanted to calculate REOC for them, I would draw the minimum bounding circle, and I would take their area in blue and divide it by the area of the minimum bounding circle in red. Okay. Again, this is the case where REAC would tell you, despite the fact that this district has like fully non-contiguous parts, separate islands, and a totally jagged border, REAC would tell you like these both look great. These are the same, which also might be a bit of a tough sell. And there are, so Stephen Selberger and Max Palmer have some work where they adjust this measure by sort of discounting the circle area for bodies of water or other states or things that you can't really district into if you're a districtor working in one state. If you're in Tennessee, you can't control for the fact that your district abuts Virginia. You can't change any districts in Virginia. So there's some ways to adjust for that, but REAC will still give you some weird results like this after you do that. Another common measure is Boyce-Clark, which deals with variation in centroid distances. So here's the intuition behind this measure. So if I start at the center of a district, my travel distance to any point on the border should be like roughly the same, right? It shouldn't take me really, really long time to get to some point on the district, but the others on the border are really close to me. So if I wanted to calculate Boyce-Clark for a pair of districts, this is what I would do. I would start by drawing a point at the centroid of each district, and then you're not seeing this here, but in the paper we actually do this for like every vertex in the district. And you draw a line to every vertex from the centroid to from the centroid to all of the vertices of the district. And then we take these and we look at the variation in those distances. Okay? So specifically we look at the mean absolute deviation of those districts. And here again, Boyce-Clark will tell you these two are exactly the same. Okay, actually this one sort of looks like a reflection of this one if you made the border ragged everywhere. So probably not the case. This, just looking at this, I mean, always, as I give this talk, always test me, right? Tell me if your mind sees this as less compact than this. I would argue that it does. But if that's not true, let us know. We'll update our data. But this is the way that Boyce-Clark works. Okay. One thing that all these measures have in common, and indeed something that almost 100 of the measures for compactness that are used in political science have in common, is that they're rotationally invariant, right? In other words, if I take a district and I flip it 90 degrees or 180 degrees, the score that REAC or length width would give it is the same every time. That doesn't matter. But is that what we really want? Is that the way that people actually perceive compactness? If the goal is to build a model that tells you how people will intuit compactness and how people will rank districts, is that what we really want to do? Is human perception actually rotationally invariant? We'll argue no, right? Here's some classic examples of this. And I'll see this rabbit, right? But if I rotate this, you should see a duck. And it's like a weird duck, because like where are its feet? Why is it standing backed into a hedge? There are lots of questions that are unanswered about this picture, but the idea is that you should see a duck in this orientation. Here, this is a much better one. This one always blows my mind. It's like 150 years old. So frog sitting on a lily pad, if you you get this.
Whoa.
Like, oh. Okay, human perception, not rotationally. You want to see it? Just get another.
Yeah, wow.
Yeah, pretty cool, right? All of that to show that human perception is not rotationally invariant. So if this is what we're going to model, we have to find some other way or find ways to get information on districts that deals with their asymmetry. Okay, and we'll do that. So human perception, not rotationally invariant. The 100 proposed measures of compactness are rotationally invariant. Okay. So they're blind to what humans perceive. In other words, if I show you these districts, right here, and now they're gone, which one was more compact? Any ideas? If you've seen this talk before, don't ruin it for everyone. Yeah, they're the same, but if you get a quick look at them, like if you show them to M-Turkers or something, for instance, this one tends to look more compact to people. Yeah.
I believe you that they're the same, but my instinct was the one on the right.
This one, yeah, right. Yeah, because it's like long, narrow. People like to penalize this. This is Nevada, right here. It's a district in California, but yeah, this looks more compact to people. So human perception, not rotationally invariant. So
Mayya, can you explain again though? Why do I care what humans perceive?
So there are a couple reasons that you want to do this. First, the idea for this part of what's happening in the law is that we get all these measures for compactness, right, that convey information. And then a judge will sit down and go, but this doesn't look compact, or it does look compact.
Okay.
So we want to, part of the goal is to be able to sort of skip the middleman and get to a model of what they're doing. So they get a statistical standard for what they're actually doing, which is this, right? And part of it is if we're also trying to model something about intent for what people are doing, we should probably stick to this perception view of what compactness is, rather than just giving you raw information on here's how round your district is. Or
So doesn't the thing about the judge suggest that we shouldn't care what, I mean, if we're trying to take this, it sounds to me like you're saying we're trying to take this out of the hands of judges. In that sense, we don't want a judge looking at it and saying, no, this doesn't look compact. In that case, the judge is relying on perception.
It's closer to the fact that we actually only care what the judge thinks. We care at the end of the day that we have a model that predicts a judge is going to look at these 10 districts and the judge is going to say, yeah, these 3 are too non-compact and these 7 are okay. So what we're trying to do is we're trying to capture exactly what the judges are going to say. And we have some slides later on that are going to show that we do a really good job of that.
The other reason that you'll see why in a second, but the other reason why we want to include this rotational invariance thing, but it's still sort of better than what a judge is doing, is that so in a judge's view, the judge is looking at a district map like right side up, and so that's affecting their like one perception that they get of this district, right? If we include a bunch of information about asymmetry and things that affect your perception of it, we're going to model how susceptible that district is a little bit better than the one look you get from one orientation of a particular district. Yeah.
So I guess it's weird. This is kind of like on the same point. It seems weird to me that we're going to come up with a measure that that 2 districts could have the exact same compactness on all these other measures, but one would be thrown out and the other one would be accepted just based on what the rotation is. And from the point of view, yes, you've modeled it very well. You modeled judge behavior very well. Is that fair? Is that like a fair thing to do?
We're not going to make any statements about.
Right, but like part of the burden of having a method for this is to come up with a measure that like helps people make fair decisions.
Right.
Or
So
the correct legal decisions.
yeah, so I think that's a good point. And there's this one thing we're trying to think about in this paper is that there's this like subjectivity objectivity tension where if we're trying to model perceptions of compactness, there's always this like weird, have we created an objective measure? So feedback on how to sort of reconcile those things is always valuable. One thing I'll say about whether or not that's fair is that the way we do this is we're capturing rotational variance through measures that I'll show you. They're actually like features of the district that are real, right? So these are features we think actually influence the way you or a judge or any human with human eyeballs will look at them and evaluate them, right? So if 2 districts are the same on a bunch of other scores, like REOC, and one is like much more asymmetrical, then that one should be perceived as less compact, right?
But again, it's about the definition of like what is the ideal standard? Is it perception, or is there like or do we need to come up with would it be better to craft just a definition of the concept, and that has some sort of normative, like has a normative bent to it that allows us to tell us like, okay, we want these kinds of districts, but not these kinds of districts. And I get that that's not exactly you're saying that perception is the way you want to go, but that has a normative implications about certain on this dimension of like we're going to go with perception. Well, that may not be particularly fair, or I don't know. It just seems strange that it seems like the law should be rotationally invariant.
It does. We
so it just seems to have a measure that it is not, that's going to influence the law seems like it could be problematic. But
To just rephrase it another way, I mean, couldn't you say, well, there's another dimension to this, which is sort of a fairness dimension? So you could concentrate on the compactness and how it would appear, but it's at least theoretically possible that you could get 2 measures that appear subjectively to the judge as equally compact, but if you looked at this other dimension of fairness, however it's defined, one may be more fair by that definition than the other. It would be nice to have that knowledge, that there's another dimension. We should maybe keep it in the background, but should dominate.
I think that's a good point, and I think that in practice, in legal cases, the discussion over compactness really is multifaceted, right? You have compactness, and then you have, like, is this district violating community boundaries? There's lots of other questions that are asked, and cases tend not to be adjudicated on the question of compactness alone, right? That almost never happens. But I think the risk of looking at compactness itself in this sort of multifaceted view of like, let's look at the fairness dimension of compactness, is that we get ourselves back into this trap where like, well, here are these 500 features of compactness that we can talk about in the case. What's more important? What matters the most to us? And we're sort of back in a world where we have lots of measures of compactness that give us lots of different information, all of which might be very valuable, but then courts have not done, like courts haven't picked, in practice, courts haven't like selected one measure that is good or one aspect of compactness that they value the most. So that's a really good point, but we just have to think about how do we balance these goals of condensing information on compactness into the one thing that the court wants, but then dealing with all of these other parts of compactness that are important.
I just want to give you one more analogy that I think may have the problem over there. Imagine we were doing this for sentencing, and we wanted to come up with a measure of like how bad the criminal defendant is. And you guys came up with a measure that really, really accurately predicted the way judges were gonna rule in the face of sentencing, right? But that might also bake in, and you might say, and like an argument might be that it may bake in a lot of like racial biases about things. But that wouldn't be a very good. So if we're designing it like a quote unquote objective measure, we wouldn't want to do that, right? We want to create something that does not necessarily reflect how a typical judge would decide one that we think that should measure things kind of fairly, right? So that's like, I think that's a little bit more. It's obviously a different setting, but that's the kind of thing the concern that I'm trying to avoid.
Yeah, I think that's important, and we'll think about that. Symmetry is, we'll think about that some more too, because it's hard to know. I don't have like a straightforward prior about whether like accounting for asymmetry is normatively good or bad, right? Like clearly racial bias is something we don't want to encode in the legal standard, but I don't know that that's true about symmetry. There's some encoding some things like length width is actually sort of negative in the sense that like if you are Virginia or Tennessee or kind of a long narrow state, then you're starting from a pretty low like possibility of compactness because you're just gonna have a lot of long narrow districts. So maybe that's not something we want to do. But symmetry we'll have to think about the normative.
I think it might be better. I mean, just like the normative motivations might be a little bit. If you put those forward as opposed to just relying on the fact that it predicts well human perception, like that might be.
I think that's fair.
But what about the origin of compactness? So implicit behind that is some notion of fairness, right? That the reason, why would they even state that they should be compact?
So I think the original intention of having compact districts was so that if I'm a state legislator and I'm trying to travel over the course of my district, you know, it's easier to do that. I can know my constituents better, and maybe also it can be a proxy for things like communities of interest. But so, as the law stands, it states that we want all these different types of fairness, and we also want compactness. So we're gonna argue that that fairness is encoded in the litigation in a series of other standards, mostly like adherence to the Voting Rights Act, and that compactness is a thing that we want just on its own, and compactness is a perception type thing, and so we're only going to focus on like how do we measure this perception-based thing.
So wait, is this argument that compactness just exists out there and it's just something we want? We don't know why?
Well, it's something that the law mandates that we have, regardless of whether we want it or not.
I mean, but surely that's built into some kind of notion of fairness.
Yeah.
It wasn't just put there for some.
Or logistics.
If it's logistic, then you should have roadways, paved roadways in your measure.
I mean, obviously that's doing with fairness, or they wouldn't be litigating it, right? I mean, the violations of it are about, you know, they're about, you know, maybe it goes hand in hand with some other violation, but.
Yeah, so you tend not to see compactness. So compactness is a thing that is distinct, that it's about shape. So maybe it's rooted in some notion of fairness. If you want to litigate compactness, if there's no like partisan or racial harms, you tend not to see people suing over non-compact districts without any other questions about fairness. So then compactness is sort of used as this piece of evidence for like, well, did you gerrymander? I don't know, does your district actually look gerrymandered? But there has to be a claim for some sort of harm, which you're right, we're not dealing with that at all here. And so there's like questions about fairness, but they're not strictly embedded in the notion of compactness as a mapping question. Yeah.
So I know you're gonna show that this like predicts pretty well, but I'm going back to that example of like the rabbit and the frog. Like what I think made that really kind of surprising is the stuff around these drawings, like the grass and stuff like that, which made it really hard to see like the changes. So I'm wondering to what degree is like this perception-based measure going to be dependent on the geometries around the district of interest? It's like what the other districts look like around whatever, like given a district, like what its neighbors look like.
Yeah, that's a great question. So I think this measure is useful for evaluating compactness when you have like a map setting or several possible map settings, because what you can do is you can use this approach to measure like so it could be like a set of districts, an entire map. And the question that you're asking is, it's hard when you're looking at a single map or a single district to think about the surroundings, because all you get, right, is the perimeter. But you can ask questions that get at your concern, which are like, well, given another set of surrounding districts, let me calculate compactness using this measure. Given past districts that have existed around this district, or given past district maps that have been used in the state, like how poorly or well are we doing, and this is going to work well for that. But like if you want to capture the surroundings, you can use this measure on the entire map, or several versions of the entire map to get at that exact question if you want to.
But I guess I'm like wondering, like, instead of like so you're showing like a binary comparison, like choose one or the other on the side. But what if like those were like stacked on each other and then like rotated another different way and like stacked on each other? Now it's like our perceptions might differ. Maybe this is like an empirical thing, but perceptions might differ based on what the surrounding geometry. So it's not like they're independent comparisons, but
So in practice, the way we propose that this measure is used is, I'm a state legislator, or I'm a judge and I'm looking at a map. So what I can do is we can use our measure to calculate the compactness for every district, and then we can look at the average compactness of all the districts in that state. We can compare that to an alternative plan with different sets of districts, and we can look at the average compactness of all of those districts, and we can say, maybe in Plan A, the average compactness of all those districts is better, so we're going to prefer this plan to that plan. So we think in practice that looking at any one district in isolation is maybe not all that useful for litigation.
That's not quite how the court cases would work. You won't sue over, if the lawsuit isn't, are we gonna go with map A or map B, it's just, is map A illegal?
Well, sort of.
But state legislators certainly look at map A versus map B.
Yeah, okay.
I think to get back to Shom's question, so if this is what you're asking specifically, when we ask people to rank districts, right, to like get the data that we're going to train this model on, they're looking at one district at a time. We don't show them an entire geography, we don't show them waterways, we don't show them like mountains, we don't show them anything like that. Under the assumption that what you're looking at, even if I show you like two districts that are stacked on top of each other, you're looking at a shape and you're essentially making the same judgment. So we're going to build the model off of the way that you perceive a particular shape, and then we're going to like the measure is going to work for that, and then we're going to aggregate the measure up if you want to think about things like arrangements of districts or geographical features or things like that. So we are having people rank images of a single district at a time. That's all we do. So maybe that answers your question specifically. In cases though, you do actually get like subsets of individual challenged districts. You get and like maps with just challenged subsets are evaluated. So you actually are like, there's lots of cases where you're just looking at one district at a time, right? Like Shaw is just two challenged districts.
So normally when judges perceive these compactness districts, do they only look at the shape of the district or also take into account how the population is spatially distributed in the area?
So when they evaluate the whole case, they look at population distribution, racial fairness, lots of issues depending on what they're being sued over. But when they evaluate compactness, the compactness question is just about
geometric shape.
That's right.
To get back to the usefulness question, I think that very few of these cases actually turn on the compactness criteria. And the reason for that is because it is a judgment call that a judge has to make. And so they're sort of chilled from holding up all of democracy's activity, right, by just their own judgment call. So I think, giving them something to hold on to, yeah, most people would agree with me, would be good. So
yeah, there's also
good to know.
I mean, the other reason we're proposing is that the fact that there's a proliferation of standards for compactness that people use creates sort of an ethical challenge in the sense that usually when a case like this is litigated, there will be two sides. One says, like, we're suing you because this district these districts are not compact and they've gerrymandered for racial reasons, and the other side says, no, we didn't. And so each side hires an expert, and expert A presents Rioch, and expert B presents Boyce-Clark, and they give you totally different information, and where do we go from there, right? And each expert also knows going in that there is some measure that will say exactly what they want to say about compactness. So there's like some need to resolve that pretty urgently too. Yeah, great questions, but we'll think about what this normatively says in terms of symmetry. That's a very good point.
So just one more question. Couldn't you just present the judge with the same district but rotated at different angles and then have them give like a score for each rotation and then take an average or some sort of, like holistic measure of what they think the compactness would be?
Yeah, you absolutely could. We get at this symmetry question in a slightly different way. We measure like that idea using something slightly different, but you could, in practice, just like survey people and rotate. You can do an experiment very similar to some of the stuff we've done in this paper where you show like a respondent several districts, but across a few districts you like rotate the same one to see how consistent the score is. You absolutely could.
And we do in fact do that experiment.
Yeah. Okay. Okay, so to account for this asymmetry issue, we include some new features of compactness in our, to train our model that will help predict what people see as compactness. One example of these measures is Y symmetry, or area symmetric reflection. The underlying idea here is that figures that are symmetric are more compact than figures that are not symmetric. So here's the other sort of answer to this question of normative implications is that we are just talking about normative implications for compactness. So the underlying question is like, at the end of the day, if I look at two districts and like one of them is like a little bit less symmetric than the other one, is it more compact? It's not a question of like, is it, because it could be the case that there are lots of cases in which making districts more compact actually makes them less racially fair and makes like population equality worse, and vice versa. So it could be that compactness has negative implications for other things we care about, and that is the case now. But the only sort of normative question is, if I make one district less symmetric, if one district is less symmetric, is at the end of the day this district less compact than this district? Like, probably yes, right? Maybe that means a lot of bad things for democracy, and that's a separate question. But that's sort of all we're dealing with here. So we're accounting for this by using Y symmetry and X symmetry. If I want to calculate Y symmetry for these two districts, for instance, I will start by drawing a point at the centroid of each district, and then just mirror reflecting each district around the Y-axis, and then taking the area of overlap, right? Taking the area where this original district overlaps with its new reflection, right? And then I divide out the area of this t-shirt and this alien spaceship over the original shapes of the districts, right? Is the way that this sort of works, thinking that larger areas of overlap mean more symmetry and are sort of better. But again, this isn't a perfect measure for compactness to be used alone. This would also tell you that these two districts are equally compact in the same area of overlap. But this is yet another feature that we sort of use in our model to figure out what people will think about compactness. Another measure we introduced to get at this idea is the number of visually significant corners in a district. The idea being that we use a computer vision algorithm applied to district shapefiles, and this computer vision algorithm identifies the important objects in sort of photos. It works the same way. So it finds significant corners in a district, and sort of districts with fewer corners are more compact. So the idea behind this is that if I asked you to close your eyes right now and draw the shape of the United States from memory, the significant features of that would be like, the Florida Peninsula, New England, sort of curve of California, but we wouldn't necessarily get every variation in the border, right? So the things that we want are Florida and the defining sort of features of the shape of the United States type of idea. So to do this, we take a pair of districts and we identify all these significant corners by running it through our computer vision algorithm. If you look at this, you might think like, oh, your lazy algorithm just like identified all the corners, big deal. It actually doesn't, to be clear. There's like this is actually an inflection point here that's not identified as significant, because you can sort of imagine drawing this from memory and doing almost as well with a straight line if you can remember that there was a kink there. Also, these images aren't high res enough to sort of show you, but there are lots of vertices that you can't see at this resolution that aren't identified as significant. Okay, so we grab all those significant corners. Both of these districts happen to have 21 significant corners, but that's another thing that we use to sort of show you like how many breaks in the perimeter that change the shape of the district there are. And so then we use all of those measures in concert to train our model. And the reason we do that is because if we do what the law has been doing, which is like let experts pick a measure at a time and go with what information that measure presents, the question is like, how do we know that we've gotten a compactness? What's more compact? If I'm trying to figure out districts that are more compact, and I take a set of districts like this, right? These are 4 districts from the Alabama State House in 2000. And I try to figure out which district is more compact. Well, if I use different standards, I get different answers. Right? If I use a measure, convex hull we haven't talked about specifically, but it's a measure that's just like a RIAC, except for instead of drawing a circle, I'm just drawing the minimum bounding hull and comparing the areas. So if I try to rank these districts according to who's more compact, convex hull is going to tell me this is the best and this is the worst. If I use RIAC, which I showed you, this is going to be the best and this is going to be the worst. If I use Polsby-Popper, which is a perimeter-based measure that just compares the perimeter of a measure to the perimeter of the minimum bounding circle, I get a totally unique set of ranks, same with Boyce-Clark, same with length width, and axis symmetry and significant corners. So I have 7 measures with 7 unique rankings for a set of 4 districts. And if you're thinking to yourself, like, well, did you cherry pick these 4 districts to get unique rankings? And the answer is yes, we absolutely did that. But it's not unusual. So we have 18,215 legislative districts in our data, right, that we use to like sample for respondents and to get features on. So there are about 162 trillion sets of 4 in that data that give you like exactly this situation, which for 7 measures, they give you 7 totally unique rankings. And lots of other inconsistencies, right, where measures tell you that really non-compact districts are really compact, or vice versa. So you get lots of inconsistencies like this. So we've got to bridge this gap. Okay, the idea of compactness is, for researchers, so complicated that we need all of those different measures that give us fundamentally different information. The law says that we need like to capture some dimension of compactness that everybody can see and that matters. And we've sort of argued by showing you these examples of districts that that's not really what the set of measures that we have for compactness right now do, right? They don't get us at this dimension, like this clearly visible to everyone idea of compactness that everybody can agree on. So we think there's truth to both of these. So there are lots of measures of districts that give you valuable information about how compact or how circular, how many arms they have, or things that are important to the way that people see compactness. But there is a single uniform dimension that we can all see that we have to measure, right? So theoretically, compactness is multidimensional. It depends on a lot of features about a district. But there is some unidimensional thing that we can see. And the one that matters is the one that people know that they can see. So how do we know when we find it? Well, we ask public officials and lots of different types of people who are involved in the districting process to do these kinds of ranking tasks. And they'll ask us to tell us whether they know compactness when they see it, and see whether or not they see the same dimension when they do this.
In other words, we're going to estimate the one dimension that is of legal interest, that is compactness. And we're going to show it has some really desirable qualities. One of these is going to be high intercoder and intra-coder reliability. That is, any two people are going to largely agree about the ranking of any set of districts. And any one person is going to agree with him or herself from time 1 to time 2 about those sets of districts. That's harder than you think. As well, we're going to show that this has high predictive accuracy. If we make a model using this measure, we're going to show that it can predict future results with high fidelity. And so how are we going to do that? Well, there are two obvious choices when we started this project. The first is paired comparisons, and the second is ranking. Paired comparisons is venerable. It's usually attributed to Thurstone in 1912, but psychologists actually know that it's as early as Fechner in 1860. Versus ranking, very old, hardly used in these processes because it's very hard. It dates at least as far back as Plato. So what does paired comparisons look like? Well, we'll give you two districts, District 1 and District 2, and we'll ask a respondent to make a choice between A or B. Then we'll give them a different set of districts, District B and C, or C and D. Some of these sets are going to be overlapping, some are going to be non-overlapping, that's important. And then we take all those binary choices and we use some kind of IRT model to construct a scale. This is how we typically do it. It's been done for decades. The problem is that in this case, this works terribly. Has terrible intercoder reliability and intra-coder reliability. This forces us to rely on a ranking, which looks a little bit like this. This is me over here sitting in that spot there. And so we print out 100 images of districts. And we're going to rank them from most compact all the way around the table to least compact over here. And we're going to take that rank, and that's going to be our ranking of compactness. That's one way to do it. Another way is in this fancy Our Shiny app that we built, where we give people 20 districts laid in this grid, and they get to drag and drop districts around until they have an ordering that fits. This allows us to do online comparisons, makes it a lot easier. We're going to show that this has really high reliability. What is high reliability? But first, we're going to argue that that paired comparisons, even though it supposedly has some better properties, is actually going to work a lot less well. So why is it better? Let's take an example with 20 districts. It's much easier to do 190 paired comparisons than it is to do pick among a set of 2 quintillion unique ranks for 20 districts. This is essentially saying if I have 100 or 20 districts and I want to pick what the right ranking is, it's basically a multiple choice question with 2 quintillion possible answers. As well, in paired comparisons, everyone does what they're good at. Respondents get to answer really easy, concrete, simple comparisons, which psychology tells us is the only thing they're good for. And researchers get to reconstruct a scale using whatever fancy IRT model they feel like using at the time. On the other hand, ranking is actually better, at least in this application, for a series of other reasons. One is that humans use time-saving heuristics. So if we go back to this over here, I have 80% of my ranking done, and I have a new district. I don't need to pick ex ante where along 100 random districts my new district is going to go. All I have to do is find which 2 districts I think it fits best in between. So that's a time-saving heuristic that we get to use. As well, 190 paired comparisons is really, really boring. We've tried doing this ourselves. Some of you in this room may have been beta testers for this procedure. You really, really did not like it. People got really angry. It was a frustrating task. It didn't work well at all. Ranking is much more fun and intellectually engaging. The people who we had do this task actually really enjoyed it. And as well, because they were enjoying it, it went quicker and they saved a lot of time. One task takes a little under an hour to do the full ranking, and 190 paired comparisons takes a lot longer than that. This we're going to argue is the most important reason. Paired comparisons allows districts to be evaluated along different dimensions. So if I'm looking at District A versus District B, I might choose to evaluate those two on the basis of how circular they are, because that's the most salient dimension at the time. But Districts B and C might be evaluated on something totally different, like perhaps the number of arms. And this makes creating a scale much harder. On the other hand, ranking forces all districts to be evaluated on the same dimension. If you're looking at 5 districts in a row, then you can't really take a new district and decide that you're going to place it there kind of orthogonally to that dimension that you're using.
Why is that true?
That's just kind of the nature of the task. Like if I have to take a district and physically like slot it in between other districts, I'm kind of like cognitively constrained to do that kind of thing. And regardless of whether or not it seems intuitive, we're going to show that it actually works out in practice.
If I took those, how many districts did you
100.
have? 100, and I laid them out here in this table. Are you asserting to me that the ones that I'm ranking over there, I would be using the exact same dimension as the ones I'm ranking over here?
Yeah, that's what we're gonna argue, or at least very, very similarly.
So a couple things we should be clear about. Like, first, when we had people do the ranking task of 100 districts, we suggested in the instructions to them that they first bin the districts by like, these are the ones that look worse, these are the ones that are kind of going on the side later, and these are the ones that are clearly the best to me. So they're starting, like every region is a set of districts that's sort of similar to them, and then they're making decisions by looking at the like 3 or 4 or 5 set that's continuously moving. So they may make like any one comparison by another dimension, and we did this ourselves a lot of times. So I'm like, I remember the psychology of this really well. So they'll decide 2 districts are circular and therefore they care about this, and they'll find one that they have to put somewhere in that set because it's in the middle, but it has 1 arm. So now they have to think about, oh, like now I have this arm. How much does this matter? Let me look at this entire set of 5 districts again and revise for the set of arms if I think they matter. So you're constantly updating the criteria that matter and integrating them when you do this with a larger set. It's not that you're like over here and then you're totally done with this and you've never seen it again. You've got your bins and you're moving within your bins and looking at a set of like 5 or 6 and reevaluating your choices.
It strikes me as a rather strong model of psychology that you're putting forth there. Maybe requires some sort of validation. I don't know.
We'll certainly show you that.
Let's talk about how to test that.
Sure.
Yeah.
I don't know. I don't think it's important here. All your point. It just seems like it's.
No, on the same point, I think like potentially you could just describe it as like people are forced to weigh multiple dimensions rather. Like I don't think I would agree. I don't think it's really accurate to assume that they're using a single dimension for all like.
So your pair comparison is done by 1 person. Have you considered like having a group of people do those pairs? Like,
oh yes, sir.
Like
we absolutely do.
Survey, and not like the Mass Organic does exactly the same thing.
Yeah. So that's exactly what we do. We have a lot of different people do this a lot of different ways. We've tried the comparisons approach for like way longer than we like to admit, simply because we kept on trying to make it work by doing different combinations of 1 person or multiple people or different scaling methods. We really couldn't find a way to make it work, as we'll show you in just a second. So we're going to look at the intercoder reliability of pairs. Again, this is 1 person's rank in comparison to another person. So here's percent agreement. Let's say we take 20 paired comparisons. This is going to be non-overlapping districts. So 40 non-overlapping districts set into pairs. And I'm going to have 1 person conduct each of those 20 binary choices. I can take person 1's 20 length binary vector and person 2's 20 length binary vector and just simply calculate percent agreement. Now, if respondents are doing coin flips for each of these paired comparisons, we expect that on average they're going to agree with each other 50% of the time, but there's going to be pretty serious tails over here. When we have M-Turkers do this paired comparisons task, that is, we give them 20 sets of districts, and we have them choose, and then we check the percent agreement between all of them, we find they do better than random, but not really by all that much. So how does that compare to when people do the full ranking? Well, full ranking doesn't produce precisely binary comparisons, but you can infer binary comparisons from a full ranking task. So if the first pair is between District A and District B, I can find where in the 100 districts District A is and where District B is, and see which of those is ranked as being more compact. That is, I'm taking my full ranking and I'm throwing out all the information besides the information that's just encoded in the paired comparisons task, and then I can measure percent agreement again. And here's what that looks like. We find that ranking does really a lot better than the paired comparisons task in inter-code reliability. Now moving on to intra-code reliability, we take the M-Turkers who did the paired comparisons task and the M-Turkers who did the full ranking task. We wait 2 weeks, and we have them do the exact same task. we did all sorts of checks to make sure they had largely forgotten these things. We got some really funny responses, including people who said, I think one or two of these districts might have been the same. But so we can do the same thing. Again, if we're expecting totally random coin flips between time 1 and time 2, we'd expect percent agreement at an average of 0.5 with tails. And the M-Turk paired comparisons people did relatively better than they did last time, but still, leaves something to be desired. When we do the same task with the full ranking of M-Turkers, this is what that histogram or density plot looks like. Again, ranking does a lot better in intra-code reliability. Great, so now I've shown largely that, yeah, Sean.
Sorry, does the ranking, the way in which you do it, does that depend on like an IAA assumption that putting whatever in the middle between the rankings like won't affect the pair? Like,
so I'm not sure I understand the question.
I think I have a similar question. It is like, so in some ways you're taking this ranking and you're saying in the counterfactual world where we had asked them to compare these two districts. Well, the ranking, this one was ranked as the 3rd best, this was ranked as the 12th best, therefore 3 would come out ahead of 12. In some ways you're assuming that if they had been given the paired comparison, they would have been evaluating along the same criterion as the full rank, when in fact, when they look at these two, they might say, oh, I'm going to use it. It's like this particular criteria that, you know, wasn't as salient in the full ranking. So in some ways, like it's not totally an apples to apples comparison.
Yeah. One way to give you a little less pause about this is that when we took the 40 districts that people did in the paired comparisons task, before we had people ranking them, we also put those 40 districts in a set of 100 with 60 totally other districts. So that's going to go a little bit of the way toward answering that, I think.
Isn't it? I mean, isn't that the exact problem that they want to solve?
Well, yeah.
Because it's like the fact that the way we would all go from the full ranking to binary comparisons, the whole point is that each one of us would do that differently.
That's exactly right. I just think,
so
that probably part of the reason that there's so much agreement that this red curve is so far to the right is, I don't know, you're making a counterfactual that isn't a very fair, or not a counterfactual, but like I don't know, the percent agreement just doesn't seem like a fair metric when that's not what the task is.
Sure. So
and it's a metric that might naturally already inflate the numbers closer to 100% agreement.
Yeah. But this is like the same person over twice. It's like
that's true.
That's what I mean. It's just like it
the
just seems like that's
density
like
plots are the same like approach. So it's just rankers to rankers between coders and pairs to pairs between coders. So you're looking at distributions of the same type of task.
I guess I meant more like the intercoder layer, not the intra.
Right. Well, so let me.
It's the same district, so they're like from the same points. Because like 100 districts, and we take, was it like 40 for the paired comparisons people, and they do 20s, but they remain in those like seated positions for the people who do the whole ranking. So they don't. It's not like we like change the amount of districts in between each pair. People see from the rank to the.
That's right.
You know what I mean? They're like still in the same spot if you seed everything in the ranking, regardless of how you evaluate them.
We can come back to this a little later if you guys still have concerns especially after the next set of slides. So, having shown more or less that the full ranking task has better reliability than the paired comparisons task, we can evaluate the full ranking task on its own terms. So here we're going to have a scatter plot. Each point is going to be one district. And this is measuring inter-code reliability. So I have ranker number 1, and this is ranker number 1's vector of rankings for these 100 districts. This is ranker 5's. We show that these ranks correlate really, really highly. 0.77. That's the median rank. This is the best quartile and the worst quartile. And here's the density plot of all of those. Again, if we're expecting completely random people, as in I give you the numbers 1 to 100 and you shuffle them randomly, we expect that to correlate between any two people at an average of 0, but with some tails. We find that people doing the full ranking task do a lot better than that. Yeah.
I'm just curious, have you taken a look at what these kind of like extreme outlier ones are?
Yeah, so we have a bunch of stuff in the paper about kind of where the residuals are and when they do better and do worse. We'll especially talk about that. We especially talk about that in the paper in relationship to the cross-validation plot, which I'll show in a minute.
Yeah, time spent on task is a big determinant of the median outlier in either case. Okay.
Is there any information on who gets it worse? Like, who are the people who are worse at judging?
People who take less time.
People
who rush through the task. Yeah.
Mm-hmm. Yeah, that's it's true. Like time spent on the task is the largest single correlate of how well you predict.
So I've got a broader question about this, which is, so as you mentioned, psychologists have been telling us that you should do paired comparisons for a long time, and then you're showing us that they should have been having people do rankings all along.
Not for everything.
Not
Well, that's my question.
Yeah.
So is it just something about compactness that's really hard for us to judge? We don't have an intuition about that?
Yeah.
So that's it. So maybe.
So yeah, it seems like when the concept is like pretty vague or multidimensional and people have a lot of latitude to interpret what they're looking for.
Yeah.
So like a complex visual or interpretation task, it seems like we've only shown this for this task, but it seems like the more complicated and like harder to define your objective is that you're asking people to evaluate, the harder it is to get reliable results from a paired comparison.
So there's some, it's slightly different though, and I mean, this is perhaps a different discussion, but the example I think of is like faces, for example, and this is something I know myself, and psychologists have done a lot of this, like people seem to be able to rank human faces on different criteria and do it pretty reliably using those paired comparisons. And maybe it's just the case that people have some sort of heuristic for faces that's we've been evolutionarily endowed with or something. But there's something weird going on with compactness because everybody seems to think they have that intuition with compactness. That's why these judges say we know it when we see it. But you're telling us that's wrong as well. Like we think we have this heuristic that works, but then we're not all using the same heuristic or something. Is what it comes down to.
That's this goes back to the slide we had a little earlier about this point here that paired comparisons allows at least compactness measured on different kind of related but slightly different measures of compactness, but the full ranking kind of avoids that.
Yeah, this would be a separate project, but I think if you wanted to have a more like methodological paper focused on that aspect, it would be interesting to do something with faces, something more abstract like beauty, right, where you do a paired comparison, and then something much more specific about characteristics of the face and see if you get the same result.
It's a great idea. Gary would love to hear that. We've tried a couple other ways or a couple other tasks to do the paired comparisons versus the rankings, and it's been a lot more ambiguous in these other cases, which is why this isn't a paper purely about like measuring stuff. But yeah, that's great. We'll definitely throw that idea to Gary and see what he thinks. So this is the inter-coder reliability on ranks. This is intra-coder reliability on ranks. As I mentioned, I take some M-trickers who do the full comparisons task and have them do it the same districts 2 weeks later. We can just measure the correlation between time 1 ranks and time 2 ranks. We see that they're pretty good. This is the median, 0.90, the best quartile, 0.92, the worst, 0.84, and the density plot. As always, we expect the correlation between 2 random vectors to be 0, but with some tails. Here we find the true observed results, obviously a lot better. Great, so now we can measure it, but can we model it? We'd like to find something of the form of this. We'd like a compactness score that's a function purely of the shape of the district. We don't care what that function is. We don't really need to interpret it. We'll try, but we don't really need to. So how do we do this? Well, we're going to collect some training data. We take 6 sets of 100 districts, so it's non-overlapping sets of districts, and we have people rank them. Each set of 100 districts is ranked by a series of people, and their rank vectors are aggregated. Then we collect some covariates. These are going to be all of the existing compactness measures: Rioch, folded copper, convex hull, length width, Boyce-Clark, a series of others. Some geometric features taken purely from the shape files, things like perimeter and area, vertices and polygons, the variance of the vertex coordinates, the variance of the edge lengths, and the new measures we develop: x-axis symmetry, y-axis symmetry, significant corners. And these are going to be the covariates in our training data. We're going to put this data through an ensemble of predictive methods: least squares, boosted decision trees, sport vector machines, random forests. Yes?
Maybe this is silly, but I'm curious how you handle different map projections here, because like the shapes, like you couldn't use the same projection for things that are in different parts of the US, like you get distortions of the shape. So I don't know how you use features like this objectively, but like I'm not sure how you handled that. I'm curious.
Yeah, it's a great question. It's one we thought really a lot about. We ended up using the best projection we could find that was the whole US. It's like a little bit of a cop-out, but we think probably it's the best we can do in this setting. Obviously, it'd be better
use
to
a single projection for every legislative district.
Yes, that's right.
Okay.
Obviously, it'd be better if we had picked, a unique state-centric projection for every state. But then you get inconsistencies in how those are done.
Yeah.
It's tricky. It's a good point. Thanks for bringing it up. We should probably mention that in the paper as well. Anyway, so as I said, we have 6 unique training sets, so we can do 6-fold cross-validation pretty easily. That is, we're going to take 5 of these sets of 100, and we're going to build a model off of them. And then we're going to use that model to predict the aggregated ranks from the held-out set, and we're going to correlate the predictions with the true observed ranks. This is one of those examples. We build a model on sets 2, 3, 4, 5, and 6. We predict the ranks by feeding it the features of set number 1, and we generate ranks. That is the x-axis. Each point, again, is going to be a district. The y-axis is the observed aggregated rankings for set number 1, and we see that the correlation is 0.91. This is pretty high, even as most machine learning tasks go, but we actually do better across the remaining cross-validation folds. Our average is above 0.93 in k-fold cross-validation. We think that's pretty impressive. Great, so we've shown that our model has internal validity. Yeah, come.
One question I have is why you didn't use, or whether you tried using computer vision software for the entire classification routine, since now you're using these sort of hand-picked features which you've taken from the literature and which you developed yourself, but what about using some sort of convolutional neural network over the entire image files? Do you just not have enough data for that?
That's exactly right. We only have 600 training sets, or observed points in our training set altogether, and that's like not quite enough for a neural net to like develop sufficient layers of features. Definitely in the future, if we end up with a lot more data, that's something we'd love to try. Great. So we showed that our model has internal validity, but what about the stuff we talked about earlier? How well of a job do we do at predicting how judges see districts? So we're going to take some respondents. They're going to be everything from ordinary citizens, people with no knowledge of districting, to those most directly responsible for it, that is state legislators, members of Congress, federal judges. And we're going to give them our shiny app we showed you guys earlier, where they move districts around using drag and drop. So we give them 20 districts. Our model produces a rank for each of those 20 districts. And then we have people rank those 20 districts, and we compare their rankings with our model's rankings. If we're doing completely random data, we expect on average they're going to correlate at 0, their rankings to our predicted rankings, but there's going to be tails. Then we collect some M-turkers and have them do it. This is how they do. They do an average pretty well. It's not great. We think that people with a little more training are going to do better. So we get some undergrads to do it. They look kind of like that. But also, undergrads, they're pretty far away from people responsible for redistricting. What about PhD students? PhD students are going to do a little bit better, but PhD students are maybe just as far away from actual redistrictors as undergrads. Maybe law students are a little closer. Law students are closer, but they're still quite far away from our object of interest. A little bit better than law students are law professors. But all these four, we're all kind of stuck in our ivory tower of academia. What about people who are like on the ground actually doing the stuff? We want some consultants maybe. These are sort of a bridge. These are the academics who are hired to act as expert witnesses and special masters. Here's what they do. But consultants, like I said, still kind of stuck in academia. What about the lawyers who hire those consultants? So we have lawyers, but who actually hires the lawyers? Well, public officials. These are the people who are physically drawing districts or ordering map makers to do so. They're right over there. But ultimately, public officials are still just kind of squabbling with each other about how districts are going to be drawn. What about the people who actually make the decisions? That is, judges, people who are responsible for determining which districts are and are not compact according to the law. Well, it's kind of hard to see because they're all overlapping, but there's judges. We have over 50 federal judges who we've given our shiny app to and have them complete this task. The average correlation between our predicted ranks and their ranks is 0.845. I think that's pretty good. Great, so now we've shown that we have a model that can predict pretty successfully how judges are going to view any set of districts. Let's do one more test. This is going to be just the eye test. So for any district, we can say how an existing measure views it and how our measure views it. There are going to be cases where both our measure and the existing measure agree that they're compact and agree that they're non-compact. But obviously there's going to be points of disagreement. A point where the existing measure is going to say that it's compact and our measure is going to say it's non-compact, and vice versa. We're going to hope to show, in this case, that where our measure and the existing measures disagree, you guys are all going to mostly unanimously agree with our measure.
Wait, before you show anything, so your model spits out like the rank ordering of a set of districts, right? So what does it mean to be compact or non-compact if it's not in relation to other districts?
To your point. So we're just gonna say the most compact for this slide. We're just gonna say the most compact quartile versus the least compact quartile. So here's RIAC. Obviously, both measures say this is compact. Seems right. Both measures say this is non-compact. Seems right. RIAC, on the other hand, says that this is in the in the most compact quartile, and that this is in the least compact quartile. I think we can all agree that this district is in fact more compact than this one. So we're going to count that as a win for our measure. This is Boyce Clark.
Can I ask them? So
yeah.
Do these latter two, do those take up the same geographic area?
I don't know off the top of my head. You mean like physical geometric area?
Yeah. So like
Probably not.
Probably not. Yeah.
Yeah.
Right. So if the one on the far right was spread out, does that matter?
Yeah, so for RIAC, RIAC is going to penalize a district a lot if it just blows up the diameter of the minimum bounding circle, right? So it could be the case that this district that looks like the two earmuffs, right, is actually really long in the middle. So,
Yeah.
or sorry, RIAC is saying this one's good. So maybe it's not very long in the middle, and it's quite non-compact, but the minimum bounding circle is small, so the area difference is small, and therefore RIAC thinks it's great.
Right.
Whereas this one's a little bit longer, so the RIAC circle would be, and anything long and narrow, RIAC is just going to tell you is terrible, even if it's a perfect box, because it just blows up the diameter of your circle.
Right.
So yes, that matters, and we're not showing you that here, but all that does go into the model. We include area.
Just a question about context. Looking at that third one, if you showed me that district and told me that cutout in the middle was around another district, I would say that's really non-compact.
Mm-hmm.
If that was around a body of water, that looks really compact. And right, that if you have water there, that's the best you can do. And that you're showing these districts just alone.
That's right.
Do you ever show them in the context of here it is with state borders and water borders to let people judge that? Because in a courtroom setting, they'd be looking at that context.
That's right. Which, going back to a point made earlier, this is why we kind of think that this measure shouldn't be used for any one district in isolation, but should be used in comparison to other possible ways to draw that district. But you're right, that we've struggled a lot with how to deal with showing people bodies of water. In the end, we've kind of decided that a district shape is a district shape regardless of what's around it, but that interpreting that out of context of what that district might possibly be is misleading. So sure, maybe if this is a body of water, I actually don't think it's a body of water in this case. Maybe if this is a body of water, then we think this is pretty compact. But could it be more compact? Maybe. Could it be a lot less compact? Probably. So that's the relevant comparison here. Anyway, so moving on from RIAC, where we left off, we were all agreeing that this is more compact than this one, even though RIAC disagrees. Here's Boyce Clark. Boyce Clark is going to say this is really compact and this is really non-compact. We're going to disagree. Length width is going to say this is really compact and that this is really non-compact. We're going to disagree again. X symmetry, this is our measure. We're going to X symmetry says that this is very compact and this is very non-compact. Again, our overall measure disagrees. If you'd like to see the complete table of this, it's in the paper. We didn't have enough room on the slide for more than these measures. So I think this is compelling. I think this shows that among as many measures as we can come up with, any one measure in isolation is going to mess up, but our measure in general does not.
To be clear, though, these are you just picked these examples, right?
So these are I picked the cases of maximum divergence. So
between the two methods.
Yeah. So the idea is among let's say RIAC. This is the district where our measure and RIAC diverge the most, conditional on RIAC score being in the most compact quartile and ours being in the least compact quartile.
I see. Okay.
So we didn't quite cherry pick it, but the conditional statements are a little bit funny.
Part of the reason we do this too is that there's also a minimum perceptible difference issue. There might be cases where one measure says kind of non-compact and they're one rank apart, where you would just never the human eye just can't register one rank difference, right?
You have a principle. You have a vaguely principled way of picking it, so it seems.
Okay. And in practice, we could pick the second most divergent set of districts, and it would look just as good. Yeah, Connor, do you have a question?
Do you have a sense of which of the existing measures gives results most similar to?
Yeah.
We do. Which one, out of curiosity, which testing measure is that?
Generally, it's pole speed popper and convex hull. They do the best. We don't include those two because they are in the paper though.
So basically, it seems that your measure is basically consistent with the idea to maximize the area while minimizing the parameter. Is that stating that?
Sorry, I'm not sure. I'm not sure I follow.
So basically, we want to maximize the area using the least sort of parameter.
I'm not quite
Is that the proper measure test?
I don't know, Maya, what do you think?
I think that's probably generally true. I think we're gonna penalize for, I know one of the things, that's an interesting point, because we have to like look at whether or not they actually do this. One of the things that rankers actually told us they were doing was casting heavy penalties for like one weird arm, or like things that jut out because they looked pretty intentional to the people ranking. So maybe with some adjustment for like the extent to which that's happening, you get an extra penalty for that. Generally, I think that's probably right. But that also falls under minimum perimeter, right? Because you would increase the perimeter by having more weird arms. So I guess that's right, even if you don't add a lot of area. Yeah.
Well, that's largely what Rocio said at the.
Yeah, I think that's right.
Yeah.
That's probably right.
Mm-hmm. Yeah.
Do you have like an idea of like feature importance? Like
we have a whole section in the paper about feature importance. And like Connor asked, yeah, certainly convex hull and pole popper are one of the most important. But X symmetry is actually pretty important up there as well.
Yeah.
Which is
Not having a ton of convexity, or like not having a really jagged perimeter, right?
Mhm.
Which makes it really long, or things people care about when they rank.
Real quick on the X symmetry thing, just to be clear, that's a rotationally invariant measure, right?
No, X symmetry is X symmetry is rotationally variant. This is X and Y symmetry are the measures we have, which are.
No, but if you twisted the district 30 degrees,
then the X
then the value is going to be different.
Right, which makes it rotationally variant.
Oh, it is.
Yeah,
Oh, it is. Oh, yeah.
Yeah.
Okay, yeah. I was
Yeah.
had stuff in my head.
If I think about this in the general way we think about measurement, that we're all trained in, we've got validity and reliability. You have a little bit of discussion on reliability. For validity, I don't know any way to evaluate validity unless I'm told what I'm trying to measure. And you haven't told us, what you're trying to measure. We know that you think it's multidimensional. Okay, that's kind of a start. That could obviously lead to different human perceptions, because if I emphasize one dimension over the other, that's going to shift my rankings in one way different from another person. And if it's multidimensional, then there's an implicit weighting, that's going on with that. So I think there's a fundamental problem here that if we don't know what, you're not telling us what you're attempting to measure, how can we evaluate validity of it?
Yeah, that's a good question.
Yeah, that's a great question. So I think we do, when we tell rankers to do this task, we give them, you could pull it up from the experiment task, but we give them a general definition of compactness, and we say it's like dense around its center, roughly, and like not irregularly shaped, which is also a very vague definition still. So people all see that and then do the task. But that's kind of the precise tension here, because compactness is not a concept that has, like a clear bar. And so the whole assumption we started with is that, right, there's no clear bar, but if we give people those vague instructions, they should all see the same thing. So validity for the context of this paper is really just, is that true or not? Because there is, you're right in the sense that like there isn't, nor can there really exist unless you pick an arbitrary standard, which doesn't really help you, a way to evaluate compactness beyond doing something like this.
Anyway, if you have more concerns, we're happy to talk about it afterwards. We definitely like to hear your feedback. Yeah, Matt.
So I was just thinking about this pairing comparison versus the ranking test, and it seems like one thing that's going on is that basically, if you think about just and maybe even helpful from a presentational point of view to like do something like this, where you have just think about two-dimensional space, right? There's 2 dimensions, and then you have different people's different implicit locations and different comparisons that they're doing, and then you can very easily generate kind of binary comparisons that cycle. I mean, you can cycle basically, right? Yeah. But it seems like the thing that you're doing by having a ranking is to say that you're going to kind of have everyone, that everyone's gonna like, there's like a common dimension that you're gonna kind of get everyone on board with. And part of that seems to be driven probably by outliers, right? The fact that they're gonna start with the big, like the ones that are clearly compact and the ones that are clearly not compact, that's gonna start to align them all into the same dimension of comparison. So I wonder if you could actually improve paired comparisons. Like if that's like the underlying drive of what's happening, like you're cutting a plane through this space and saying like that's the plane that we should all be loading on. Then maybe what you could do is you could actually start out paired comparison by doing like obvious ones first, and then like kind of like a GRE type thing where you kind of slowly get harder and harder. And like I wonder if you could induce higher levels of higher rates of intercoded reliability and intercoded reliability by doing something like that. Which is kind of, it's similar to the task that you're doing by the ranking. It's kind of implicitly what you're telling them to do, but you might be able to save time. You know, there may be, you may get some of the advantage of paired comparison that way.
So one of the first specification actually we tried of doing paired comparisons was we would take, we took 6 districts that we thought were basically like evenly spaced across the entire compactness dimension, which we thought should be like some pretty easy comparisons. And we found that people really didn't do well on that task either. So I don't think it has to do with like the ease of the task or you know, priming people with really obvious comparisons, because like probably, you know, between any given quintile of the compactness dimension, it should be pretty easy to distinguish between any two.
I think so what you're suggesting I think will certainly improve paired comparisons. I think the 2 problems we still have are, first, if people are just, part of what's different about the ranking task is that people can actually like look at multiple districts for reference. They don't have to hold multiple dimensions in their brain at once to do one comparison, because they're still like looking at a set of 2 compact or non-compact districts. They start and end, and they try to evaluate them. And they say like, okay, like here arms are important. Then they go to the next pair and they're kind of more circular, and they say like, well, this one's more circular. Oh, but now I have to adjust for this, and they can't go back, kind of a thing, unless we like let them go back. And I think that'll just be
ruinous.
Infinite cycling, which is sort of less helpful. And it doesn't help the fact that for some reason, I don't know if you know any good reasons for this in Psych, Ryan, let us know. People really like got burned out on the paired comparison task really fast, and they just told us that like 3 or 4 later they were flipping coins, and that didn't happen to us, even though it's like more of a time suck. If you sort of think about the nature of the task, they didn't do this when they had to rank districts, and I don't know why that is, but they just like really copped out really fast.
I mean, it actually like was
Yeah,
enjoyable
it was more
to
fun.
do.
Yeah.
Was that something you saw on MTurk, or was it just?
So before we put an app version of this on MTurk, we like piloted it on our friends to make sure it works on everybody's machine and all this. And like, we had them, and they were like, I am enraged after like every single person we tried this on would just G-chat us and go like, I hate you, and I don't want to do this anymore. And after the first 3, I just flip coins, and this is too hard.
But you didn't try that on, you didn't do the paired comparison on MTurk, or you did?
We did. And we got nonsense.
I don't know, I mean, that's kind of,
consistent with that.
it's a little bit back to the question I asked earlier, where it seems like people have used these paired comparisons successfully, though.
Yeah.
So maybe your friends have just like little short attention spans or something. I'm not sure. I mean, it's possible, you know.
Steven, I don't know.
Well, it's like, I mean, it's just a different criteria than because often subjects are, you know, so maybe like you didn't ask them Turkers what they're doing, but they're like, they're getting paid, so they're not as.
You paid me 15 cents an hour. I would have
That
paid a lot more attention.
Yeah. So 2 questions. One, did you make any attempt to assess whether machine learning methods did a lot better than sort of traditional stuff? And
So
and then second question is, have you thought about doing some hierarchical models to see whether people are bringing different coefficients on different dimensions?
That's an interesting idea. So to your first question, yes, we've tried. We've compared the predictive accuracy of just like a vanilla OLS to the accuracy of the model, and it's pretty. It's not like world changing, but it's substantial. It's like 4 or 5 percentage points of predictive accuracy, which is pretty good for OLS, right? But we'd argue that those 4 or 5 points are actually pretty notable. As for a hierarchical model, that's an interesting idea. We have not thought about it. Definitely something to think about. We're always interested in other ways to think about like feature weighting.
I mean, it does seem that would help you figure out, is there really a single concept there, or different people have different concepts?
Yeah. Well, yeah, go ahead.
So if the idea is to be able to have some idea of predicting how the judges would make these decisions, like, do you have some concept of like how they are actually deciding this? I imagine they're not like, okay, District A versus B, you know, and then B versus C, right? So it seems like they're probably looking at these districts in relative isolation and then looking at some other possibilities, right?
So it depends on the case. There are definitely cases where they're basically they're usually looking at a whole map with like the district highlighted, and they'll say like, look, this section of the district, they don't have like a folio they're flipping through where they have like 15 possible versions of the district.
Yeah.
They'll look at a picture of the district as it is, sometimes a picture of the district in the map like as it was before the plan was implemented, and they'll say like, oh, this thing makes it less, like this thing you added that you jutted out like makes it less compact or not. So that's like typically what's going on.
Well, yeah, it is 1:30. I mean, I was on the, concluding slide anyway. So thanks, guys. I appreciate it.
Thank you. Thank you everyone for coming, and I look forward to seeing you next week.
And Maya and I will stick around if you guys have any other things you'd like to talk to us about. I'll stick around.
Yeah. The reason I asked is in university making those decisions in the same way. You're clearly showing that the decision process itself is kind of determines the outcome.
I do what you're saying, yeah. So yeah, in practice, like they're looking at like
Yeah,
they're evaluating.
Yeah, you saw a pretty early version of this guy.
Even if it's a set of districts or challenge, it's like, is this one? So it's just a question of like, how do we take this thing? The way that we set the model up is different. We use set the model up in a way that it'll tell us.
I mean, they were at the top. The PhD students were at the top. But they were like 0.845. So, like, I think all the different.
We can, if we train the model,
But like they were all so close within like if you did a t-test
we know what the approach
to like see which of these two districts are different.
We know whether you think it's compact. We know what it's for a single district. So it's like okay. Yeah.
When I read your paper, I thought about this, and I still don't know what the suggestion is. But it strikes me that like you could apply this method to if it's at all useful to have like a baseline on how compact things are in the state. You could apply this model to all like the county maps, something that's invariant to technical processes. So either like the county maps means like Western states is not gonna help because they're all squares. But like in the east, like you could imagine like saying, you know, this district map is like this score, and the counties, which like we think, well, I guess that's not true, but like counties are generally pretty compacted, squared off. Like this is how it appears within the state. Like and in some sense, that like this is like the county map is also constrained by things like Maryland with a weird border that's skinny and whatnot, and so you could say like the county map in Maryland is, you know, this good. The state legislature map is worse or better than the county map. Like it's a baseline.
That's a great idea.
Yeah. Or I mean, counties you have. I mean, there's not a lot of other invariant things. I was thinking precincts, but the trouble with precincts is that it's precinct in a lot of states are constrained to be no, not even within. Well, they're constrained within counties, but they're also constrained to be within the legislative districts.
Right.
Like certain states have laws that you can't split a precinct between two state houses. So a precinct has to be fully situated within one congressional district, one state house district, one state legislative district. And so when that happens, the boundaries of the precinct are necessarily bounded within the district as a whole. Although you could maybe do interior precincts if there are those.
I think
that's maybe
I think counties is the way to go. Yeah, that's a great idea.
Yeah, just like a baseline of like how compact can you be given the geographic features, the water features,
I also think could be
part of a response. You want it to be something where
kind
of dodge the question
is fair or not, or whatever. It's like
because it's like we're agnostic. Like I don't in many cases imposing compactness for certain is unfair. Like actually, because we have a graph too that shows that like that in the paper imposing compactness actually does Or it ends up being like
I like the
sorry,
stuff
the other way.
and
So
it
so
actually
equal
was, I did
population
actually
collection
enjoy doing
tailored
it.
compact.
The ranking was fun,
Yeah,
like,
it's not exactly
you spend like
Yeah, I did
20 or 30
too.
minutes in playing around, and it's kind of
The
cool.
way I did, I remember, I was having trouble, and then I decided to bid them, take, so, okay, these are the ones that are most compact, these are the ones that are least compact, and within the most compact,
Yeah,
there's
and then just deal with it, like middle, the edge cases, like.
That's one of the unintended benefits of having it be like 5 by 4
regardless of whether
rows.
that's a good
Is that you have like the most compact row, the second most compact row,
And then the
you
second
can
thing
kind of just like
ultimately
What's in there, and then all you have to do is just check that
And so in the Ocean you have actually, as you saw, there's round 1, which is a 5 by 4 grid, and there's round 2, which is just a vertical row. And so that then you can like give a validity check where you can check each pair all the way down. Yeah.
Yeah, and that's ultimately what we're
So it's not that you're suggesting this as a
Good job pulling it
measure,
together.
it's
Very.
that
I think it helped you guys. That was like basically your Pullman test,
Yeah,
right?
I think
Yeah,
that's right.
it was basically
Yeah, and we like
I think things
we
got
do a
a
better
little
job
lost.
in the
So
paper of doing that because
A lot of
we have
questions
to talk a
about
lot
that.
more
So
about
the
the law
frame,
than we
right,
typically
is-
Chris missed my talk twice in a row.
But yeah, that's a
I had a meeting at
It
noon
just
that
seemed
I
like
forgot
that
about.
ended up being big.
The one day or like heads up was,
Yeah. Yeah, and I think that's also ultimately the answer to Matt's question in my
But
mind, but like,
so the frame,
I,
right? Like, let's
if
help.
we sort
let's
of are
help
comfortable with
judges.
that, we're only talking about compactness,
don't like
this
it.
isn't a question about anything else.
I'm not
It's
thrilled
fairness.
with it.
The question is just, does imposing this
a couple,
expectation
like,
that symmetry
because you
makes
got
you
the
more
question, why
compact,
do they
is
need
it
it?
like
Yeah.
fair for the
And,
context of compactness, or symmetrical
and
shapes
so I
like
tried to give you a
better
little
at
help,
compactness
that
than
like, they
asymmetrical
need
shapes?
this because
Yeah.
they don't use it
Probably
as much
are.
as they should.
Right.
They're
I
being
think you should
actually
sell it
should,
as a tool,
right?
not a
And
standard.
a great
you can
point.
make
I
maybe
agree, yeah.
But I think
That's so
So if
actually,
you're a tool,
Yeah.
then
maybe
you
an
don't
even
have to be
better
fair.
argument
If you're
is
standard,
that
then you wanna be fair.
none of these cases come
I think that's
to a judge free of political context.
Right.
Right?
I think
And,
you made that
and
point
so
there,
what, so what you need this for is judicial control. Like you need to
Of
control
course,
the
yeah.
judges and make sure that they're not like futzing standards when it benefits their
Okay.
political cause.
Yeah, that's
Right.
also very true, like, so like, one of the cases we worked on,
I did, yes.
this
Okay,
whole
I
debate
didn't
over
receive it,
everything,
so-
like,
If
we
you
were
send me an
working
email,
for the
then I
Republicans
can
to
add you
defend
to
a
the
map
list.
in a state
did
with
you
a
receive
Democratic
your
government,
Cantor's
governor who was
email?
like,
I believe
defend
so.
the map, but like, do
And,
a shitty job.
then,
So that
that
my party
should've
would
been
have,
added
right, 'cause, like,
me
then
and,
she
uh,
got
yeah,
to
of
try, and we
course,
were like,
and
what?
again,
And then he was
they're
like,
all
oh, we're gonna stop
Oh,
paying.
okay.
Right.
So
Maybe
this
if
is
it
like a
wasn't a
whole
test,
thing.
then I might not
It was
have
like
done
a,
that.
such a deeply unethical whole process.
And can I
Yeah,
put
it
down
is.
the
Like,
chat?
our sort of first stop is that like this proliferation of measures means terrible things for, because I don't care whether compactness is true, and in most cases I think compactness actually is bad for things like population equality and racial
What
equality.
about PR?
But it's good, it's
Wait,
good
as
for-
long as we're trying to
Okay, so
convince
I'll add
judges
that.
to do something, why
Right.
don't
Thank
just
you
simply
for coming.
convince state legislatures to move to a PR system?
Well, yeah, yeah,
That would end all this trouble.
yeah, well,
There are a lot of individual ways to end the trouble. But
yeah,
I
there's
think,
like lots of radical solutions that would work that have nothing to do with this, but I don't
But
think districting
PR is much more democratic than all of the other ways of doing it.
Yeah,
Yeah,
you
true enough,
know,
true enough.
you end up with the effectiveness of a solution is inversely proportional to how likely it is to happen.
Yeah, exactly, exactly.
Well,
I mean, I've got some
what would be
question
really
about the
cool is if
ecology
you
of
could- I mean,
it.
you can
Yeah,
sort
And
of see that showing
did you
effect from
adjust
something
the index
like
for the
illustrate that
pairwise
there is a
comparison?
showing effect,
Because
like,
you
to
know,
that,
their continuous value, if you have
like-
a continuous
like,
value,
talking to a judge would be nice, right? Like if a
higher
judge-
but
If I had a
you
conversation with a judge
link
where they said something like,
up to their
yeah,
binary,
I tend to ignore
the
compactness because,
correlation
you know,
becomes
for
lower.
sure.
People-
It's totally
people-
in
So we,
no
let's
guidance,
see, we do
right?
adjust in the
And
sense
I'm
that
very
when
reluctant to
we convert
substitute my
the
check.
rankings
So it's
to pairwise
chilled,
comparisons
but it
to
also
compare, so all we're
might be
reporting
being
is
used as
the like
a sword
0-1
when
decision of whether in
oh
the
yeah,
ranking,
yeah. So
the,
when it
judges,
shouldn't
so
be.
like,
judges either
district
don't
A
use
is
it
in
or they use it
fact
to their
less
political
compact.
advantage.
Yeah, like a
And
sword
then-
or a shield.
Right, so that's
for
all we're
political-
reporting. We're not reporting
Like,
the correlation.
sure,
of the
it's
entire
racially
ranking to
horrible,
compare.
but it's
Okay,
compact.
so,
Right.
so in your ranking comparison,
Right. And so we did kind of
So when we
observe
compare
stuff
like
that, right?
rankers to
Like that was that was like a Supreme Court case where they were like,
So,
yeah,
you're
I
talking
mean,
about in the graphics. I think
where
we do
the-
this.
the
I think we
quote that
actually
Maya read
we.
about,
I
like,
don't know if that's off
you know,
the top of my head.
we
if
should
that's
know
the
when we
graphic
see it,
showed,
but
in
really,
the
if you
paper,
see
we
it, then like
definitely
there's probably
show, like,
something
well, what
else.
happens if we
Right, that's like
reduce
basically it's like an
basically this
example of
like
what that.
continuous
Yeah.
ranking
here's a
variable to just
question.
0
Another
1s for
one,
whether
like
or not
to kind of
pairwise comparisons
push-
are correct
push
relative
those
to the other
Sure.
people that rank them, and we show that correlation.
So you run
I
the
don't know if that's the plot we
summaries and
showed
then they
here,
clean up
but we also
afterwards?
do this.
Okay.
Yeah, because we like
That doesn't
recognize
seem
that
fair.
somewhat.
Sorry,
Like,
so
is it
yeah.
important to
Thank
be
you.
right about things that everybody agrees are compact?
Oh yeah.
Or is it important to be right about the borderline?